Where are alkali metals and where are they located in the periodic table? Alkali metals are a group of highly reactive metallic elements found in group 1 of the periodic table, comprising lithium, sodium, potassium, rubidium, cesium, and francium, positioned on the far left side of the periodic table, excluding hydrogen. These elements share a single s electrons in their outermost shell. Example: sodium 3s1. This electron configuration makes them eager to lose that electron to achieve a stable noble gas configuration, resulting in a +1 oxidation state and a strong reducing properties. Their reactivity acetates down the group due to a decrease in ionization energy caused by increasing atomic radius and reduced nuclear attraction, as seen in the violent reaction of cesium with water, producing cesium hydroxide and hydrogen gas. 2 cesium plus 2 H2O is equal to 2 cesium hydroxide plus H2O. What are alkaline earth metal and what makes them different from alkali metals? Alkaline earth metal located in group 2 including beryllium, magnesium, calcium, strontium, barium, and radium. Unlike alkali metals with one valence electron, these elements have two electrons in their outermost s orbitals. Example: magnesium 3s2, neon 3s2, leading to a +2 oxidation state. This dual electron configuration requires more energy to remove both electrons, making them less reactive than alkali metals, but still highly reactive compared to most elements. They form stable ionic compounds. Example: calcium chloride, and show increasing reactivity down the group due to larger atomic size and lower increasing reactivity down the group due to larger atomic size and lower ionization energy, though beryllium's covalent tendencies set it apart. What elements are included in groups 3a to 7a of the periodic table? Groups 3a to 7a, UPAC groups 13 to 17 encompasses a wide array of elements. Group 3a include boron and aluminium, metalloids and metals. Group 4a has carbon and silicons, key non-metals and metalloids. Group 5a features nitrogen and phosphorus, non-metals with varying allotropes. Group 6a contains oxygen and sulfur, essential non-metals, and group 7a, the halogens, includes fluorine, bromine, iodine, and astridine. Highly reactive non-metals. These elements' properties range from semiconductive to diatomic gases, nitrogen, oxygen, and corrosive liquids. Bromine, driving by 3 to 7 valence electrons and their position in the p blocks. Why are halogen highly reactive? Halogens in group 17 are highly reactive due to their electron configuration with 7 valence electron. Chlorine uh, is equal to neon 3s2 3p5, one short of a stable octet. This drives them to gain an electron to form -1 ions. Chlorine or share electrons in covalent bonds as in HCl. Their reactivity peaks with fluorine and the most electronegative elements and decreases down the group fluorine, chlorine, bromine, iodine due to increasing atomic size, which reduced electron affinity and strengthens XX bonds. Example, F2 is weaker than I2 due to lone pair repulsion. They react exothermically with metals 2Na plus Cl2 is equal to 2NaCl and HCl, and hydrogen 2NaCl, 2Na plus Cl2 is equal to 2NaCl. Why is metallurgy and what is its purpose? Metallurgy is the scientific and technological discipline dedicated to extracting metals from their naturally occurring ores, minerals, compounds like oxides and sulfides, and refining them into pure or alloyed forms suitable for use. Its purpose is multi-phased. It involves processes like crushing, smelting, and electrolysis to isolate metals. Example, iron from hematite. Access their physical properties. Example, ductility, conductivity, and optimize their applications in industries such as construction, steel, electronics, copper, and aerospace, titanium. It also addresses environmental concern like sludge disposal to ensure sustainable metal production. How is magnesium extracted from its ore? Magnesium is extracted from ore such as magnesite MgCO3 or dolomite CaMgCO3 through a detailed process. Initially, the ore is calcined at high temperatures around 700 to 1000 degrees Celsius to decompose it into magnesium oxide and carbon dioxide. This magnesium oxide is then converted to magnesium chloride MgCl2 by chlorination with hydrochloric acid or reaction with ammonium chloride. The final step employs the Dow process where molten MgCl2 is electrolyzed in a steel cell with a graphite anode and iron cathodes, reducing magnesium 2 plus to magnesium metals at the cathode while chlorine gas evolves at the anode. The resulting magnesium is used in lightweight alloys for aircraft and automotive industries. What is the primary ore for aluminium and how is it processed? The primary ore for aluminium is bauxite, a complex mixture of aluminium oxide Al2O3 and impurities like iron oxide. Processing begins with the Bayer process. Bauxite is pulverized mixed with sodium hydroxide under high pressure and temperature 150 to 200 degrees Celsius, dissolving aluminum hydroxide into sodium aluminum after filtration to remove impurities. The solution is cooled to precipitate pure alumina Al2O3. This alumina is then refined via the whole Herold process and Electrolytic method using a molten cryolite Na2AlF6 bath at 950 to 980 degrees Celsius, where alumina dissociates and aluminium is reduced at the carbon cathode with oxygen reacting at the anode to form carbon dioxide, yielding high purity aluminium for packaging and construction. How is iron extracted from its ore? Iron is extracted from hematite Fe2O3 or magnetite Fe3O4 using a blast furnace. A towering structure operated continuously. The furnace is charged with ore, coke, carbon, and limestone CaCO3. Preheated air up to 1200 degrees Celsius is blasted in igniting coke to produce carbon monoxide and heat. Carbon monoxide reduced iron oxide to molten iron, while limestone decompose into calcium oxide and carbon dioxide, with calcium oxide forming sludge by reacting with silica impurities. Molten iron settled at the bottom, tapped periodically, and is further processed into steel by adding carbon or alloy, serving as the backbone of infrastructure and machinery. What are the common oxidation state of transition metals? Transition metals groups 3 to 12 exhibit multiple oxidation states due to the involvement of d electrons in bonding. For instance, iron commonly shows +2 iron 2 plus, example FeCl2, and +3 Fe3 plus, example Fe2O3. Copper displays +1 Cu2O and +2 Cu SO4, and chromium ranges from +2 Cr Cl2 to 3 plus 3 Cr2O3 to +6 CrO4 2 minus. This versatility arises because a d orbital can lose electrons or participate in hybridization, enabling diverse coordination of compounds and catalytic roles, such as manganese +7 state in KMN O4 used as an oxidant. What is aqueous chemistry in the context of transition metals? Aqueous chemistry of transition metals explore the behavior of their ions in water, where they typically form hexa-aqua complexes. Hexa-aqua complexes, example FeS2O 6 2 plus or CuS2O 6 2 plus, due to waters along pair coordinating with the metal. The field examines solubility. Example FeS2O 6 3 plus hydrolyzed to form acidic solutions. Solution redox reactions. Example Fe2 to Fe3 with oxidants and ligand substitutions. Example Ni Es2O 6 plus 2 plus 6 NH3 is equal to Ni NH3 6 plus 2 plus 6 S2O, often accompanied by color changes. These properties are critical for understanding their roles in catalyzed and analytical chemistry. What are oxides and halides of transition metals? Transition metals are oxide formed by reaction with oxygen. Reaction with oxygen includes FeO3 rust plus 3 state, CrO3 plus state strong oxidants, and TiO2 plus 4 state a white pigment. These vary from ionic two covalent example CrO3 based on oxidation state and metal size halides resulting from halogen reactions include Fe Cl3 covalent plus 3 TiCl4 covalent plus 4 used in polymerization and CuCl ionic plus 1 their properties color magnetism and reactivity depends on the metal electronic structure making them available in pigments catalyzed and material science. What are lanthanide and where are they found in the periodic table? Lanthanides are the 15 elements from cerium. Cerium Z is equal to 58 to lutetium. Lutetium Z is equal to 71 positioned in the A block at the periodic table bottom. Following lanthanum, their 4f orbitals fill progressively. Cerium Xe 4f1 5d1 6s2 to lutetium Xe4f14 5d1 6s2 leading to similar chemical properties due to lanthanide contraction found in mineral like monazites. They are critical for magnets in the phosphorus lasers despite their rarity and complex separation. How are lanthanides isolated? Lanthanides are isolated from bodies like monazite, a phosphate mineral, or bastnasite, a fluorocarbonate through a multi-step process. The ori is digested with sulfuric or hydrochloric acid to form soluble lanthanide salt following by precipitation to remove impurities. Separation release on ion exchange chromatography where lanthanide ion are differentially adsorbed onto a resin and eluted with complexing agents. Example citrate or solvent extraction using organic solvent exploiting a slight ionic radius differences due to lanthanide contraction. What are aqua ion and oxo salt in lanthanide chemistry? Aqua ion are hydrated lanthanide complexes such as CeS2O8 3 plus or GdS2O9 3 plus formed when lanthanides dissolve in water with coordination numbers 8 9 reflecting their large ionic radii and high charge. Oxo salts like lanthanide oxalates Ln2C2O4 3 or nitrates LnNO3 3 arise from reactions with oxo acids often as precipitates in purification. These compounds highlight lanthanide's preference for oxygen donors and high coordination influencing their use in catalyst and optics. What is a coordination of compounds? A coordination of compounds is a complex where a central metal ion or atom CO3 plus Pt2 plus is surrounding by ligands molecules or ion with lone pairs NH3 Cl minus H2O forming coordinated covalent bonds. Examples include CONH3 6Cl3 where 6 NH3 ligands coordinate covalents and the chloride ion are counterions. These compounds exhibit unique properties like colors, magnetism and stability played a role in catalysis. Wilkinson catalyzed medicine, displating and inorganic chemistry. Hemoglobin. Who developed the nomenclature for coordination of compounds? Alfred Werner, a Swiss chemist pioneered the nomenclature and structural theory of coordination compounds, earning the 1913 Nobel Prize in Chemistry. His groundbreaking work in the late 19th and early 20th centuries proposed that metal exhibit a primary valency oxidation state and secondary valency coordination number, explaining complexes like CONS3, 6Cl3. His insights into stereochemistry and isomerism laid the foundation for modern coordination chemistry. What is the Warner's primary valency concept? Warner primary valency concept define the oxidation states of the central metal ion corresponding to the number of negative charge. The number of negative charge it valence in the coordination spheres, outer spheres in CONS3, 6Cl3, cobalt plus 3 oxidation states. Primary valency is balanced by three chlorine ions, chlorine ions reflecting ionic interaction. This valency determines the compound's overall charge and is distinct from the coordination number, providing a framework for understanding ionic versus coordinate bondings. What is the secondary valency in coordination compounds? Secondary valency or coordination number is the number of ligand donor atoms directly bonded to the central metal ions via coordinate bonds for CuNH3 for 2 plus. The secondary valency is 4 as 4 nitrogen atoms form nitrogen atoms form NH3 ligands coordinate with Cu2 plus, typically forming a square planar geometry. This valency dictate the complex shop octahedral for 6, tetrahedral for 4, and influence stability often ranging from 2 to 12 depending on the metal and ligands. What is the Seedwake electronic concept? Seedwake electronic concept developed by Neville Seedwake explain coordination compounds formation through the donation of electron pairs from a ligand lone pair to the metal ions, empty orbitals forming dative coordinate bonds for NiCO4 carbon monoxide lone pairs donate to nickel 3d and 4s orbitals, stabilizing the complex. This effective atomic number an effective atomic number rule where the metal acids noble gas configuration complements Warner's structural model, enhancing understanding of bonding and reactivity. What is the valency bond theory in coordination chemistry? Valency bond theory VBT proposed by Linus Pauling describe coordination compounds. Describe coordination compounds formation by the hybridization of metals orbitals with ligands orbitals in CONS3 3 plus CO 3 plus 3D 6 uses inner 3D 4s and 4p orbitals to form D2sp3 hybridization, accommodating 6 NS3 ligands in an octahedral arrangement. This theory explains geometry and paramagnetism. Example: high spin versus low spin complexes, though it's limited by its inability to predict spectral properties accurately, later defined by crystal field theory. What factors affect the stability of coordination compounds? Stability of coordination compounds depend on several factors. The metals ion charge and size. Higher charge density, example CO 3 plus increases stability, ligand strength strong field ligands like Cn minus versus weak fields like H2O, and environmental conditions, psi temperature, the silage effect using multi-dentate ligands like EDTA enhance stability by forming multiple rings, releasing entropy stability constants. Example log K for efficiency 4 minus 24 for quantify these influencing applications in solution therapy and catalysis. What is isomerism? Isomerism in coordination compounds. Isomerism in coordination compounds occur when the same molecular formula yields different structures, geometries. Isomerisms. Example cis PDNS3 2 versus trans arises from ligand position difference. Optical isomerism. Example CO EN3 3 plus enantiomers from serology linkage. Isomerism. Example CONS3 5 NO2 2 plus versus CONS3 5 ONO 2 plus from different ligands. Attaching a point and ionization isomerism CONS3 5 SO 4 Br versus CONS3 5 Br SO4 for my interchangeable counterions. This variation impact properties like color and biological activity. However, coordination of compounds used in biological system. Coordination of compounds are integral to biology. Hemoglobins Fe2 plus center coordinates with oxygen coordinates with oxide and histidine in a hemicomplex enabling oxygen transport in blood. Chlorophylls Mg2 plus is coordinated by a porphyrin rings for photosynthesis, converting light to energy. Vitamin B12 CO 3 plus coordination facilitates methyl group transfers in metabolism. These inorganic rules highlight the importance of metal ligands interactions in life processes with applications in mimicking these systems for drug design. What are inner gases and why are they called inner gases are noble gases group 18 helium, neon, argon, krypton, xenon, radon are called so because they are closest shell electron configuration. Example neon 1s2 2s2 2p6 provide exceptional stability with field S and p orbitals. This complete octet or duet for helium minimizes their tendency to gain loss or share electrons, rendering them unreactive under standard conditions. Exceptions like xenon fluoride with fluorine under UV light occur due to xenon's larger size and polarizability, but their inertness suits uses like shielding gases. What are some applications for inner gases? Inner gases have specialized gases. Helium cools MRI magnets and lifts balloons due to its low intensity. Neon glows in sign via electric discharge. Argon shells whales and fails incandescents balls preventing oxidation. Krypton enhance laser precision. Xenon powers high intensity lamps and medical imaging. Xenon 133 and radon dissipate radioactivity. Treats cancer via targeted radiation. Their non-reactivity ensures safety and efficiency in these applications. Why does xenon show some chemical reactivity? Xenon's reactivity rare among noble gases stems from its large atomic radius 216 pm and available 5d orbitals, allowing it to overcome its stable krypton 4d 10 5 s2 5p6 configurations under extreme conditions. Example, electric discharge with f2. It forms compounds like xenon fluoride, XeF2, XeF4 and XeO3 by accepting electron pairs from a highly electronegative fluorine or oxygen. This polarizability and electron accessibility distinguish it from lighter, less electron noble gases. What is the general trends in reactivity of alkali metals? The reactivity of alkali metals increases down group 1 lithium to cesium due to the decrease in ionization energy from 520 kilojoule per mole lithium to 376 kilojoule per mole cesium. As atomic size increases and nuclear shielding weakens the hold on the valence electron. These trends manifest in a reaction with water. Lithium reacts slowly while cesium explodes, producing MOH and hydrogen. Example, 2K plus 2S2O is equal to 2KOH plus S2. Lower melting points and higher electrode potentials down the group further enhance reactivity. However, chromium and nickel extracted chromium is extracted from chromium FeCr2O4 by roasting with sodium carbonate, Na2CO3 and oxygen to form sodium chromate, Na2CrO4, which is laced and reduced with aluminum in the alumino thermic process, thermite reaction to produce pure chromium. Nickel is extracted from pentallandite nickel iron 9s4s8 by roasting to nickel oxide NiO, smelting with a matte copper nickel sulfide and electrolytic refining, yielding nickel for stainless steel and battery electrodes. What is the role of copper in metallurgy? Copper is extracted from chalcopyrite CuFeS2 through smelting to a copper matte Cu2S, followed by converting with air to blister copper and electrolytic refining to 99.9. What are the common oxides of lanthanides? Lanthanides form stable oxides due to their blast 3 oxidation state, including CEO2, cerium 4 oxide, a catalyzed in auto exhaust systems, Nd2O3, neodymium oxide, a glass colorant, and La2O3 lanthanum oxide used in optical lens. These are produced by igniting lanthanide metals or carbonates in oxygen exhibiting high melting points, Nd2O3 at 2270 degrees Celsius, and unique 4f electron properties, making them available in ceramics and electronics. What is the coordination number in CuNS342 plus? The coordination number in CuNS342 plus is 4, as 4 ammonia NS3 molecules act as monodentate ligands, is donating a lone pair from nitrogen to Cu2 plus. This typically results in a square planar geometry favored by D9 Cu2 plus due to John Taylor distortion with bond lengths around 2.0 angstrom. The deep blue color of the complex arises from DD transitions used in qualitative analysis for copper. What is a Select effect in coordination chemistry? The Select effect is the enhanced thermodynamics stability of coordination of compounds with multi-dentate ligands. Example: ethylene diamine in or EDTA that form select rings with the metal ion for NiEN3 2 plus 3 in ligands create 5-membered rings, releasing more water molecules, higher entropy than NiNS3 6 2 plus, increasing the stability constants log K is equal to 18 versus 8. This effect is crucial in sequestering metal ions in medicine and industry. How do actinides differ from lanthanides? Actinides thorium Z90 to LR Z103 differ from lanthanides by their greater radioactivity. Example: uranium 238 Pu 339 Dk. More variable oxidation states, plus 3 to plus 6. Example: UO2 2 plus. And 5f electrons that are more diffuse and available for bonding than 4f electrons located after actinium. They are synthetic beyond uranium, used in nuclear reactors. Uranium Pu and weapons constructing with lanthanides, non-radioactive magnet relate applications. What is the geometric isomerism in coordination compounds? Geometric isomerism occurs when ligands could be different special arrangements around the metal. Example: in PDNS3 to Cl2, the cis isomers has Cl ligands at 90 degree adjacent, while the trans has them at 180 degree opposites. This affect properties like dipole moments. Cis has one, trans does not. And biological activity displating is anti-cancer, transplating is inactive with geometry determines by coordination number and ligand size. What is the role of zinc in metallurgy? Zinc is extracted from sphalerite zinc sulfate by roasting to zinc oxide, then reduced with carbon in a retort furnace or electrolyzed from zinc sulfate ZnSO4 solution. Its primary metallurgical role is galvanizing steel, forming a protective zinc layer 0.1 to 0.2 millimeter that corrodes preferentially, expanding steel life in construction. It's also allowed in brushed CuZn and used in die casting for automotive parts. Why are transition metal oxides colored? Transition metal oxides are colored due to the electron transition in the metals partially failed d orbitals split by ligands. Ligands are failed in a crystal field or molecular orbital theory context for CuS2O6 2 plus D9 absorption or red light 600 to 700 nanometer causes a blue appearance with the extract color green for nickel oxide, yellow for CrO3 depending on oxidation states, ligand strengths and geometry, making them useful as pigments and indicators. What is the oxidation states of iron in FeCl3? The oxidation states of iron in FeCl3 is plus 3 is chloride ion. Chloride ion contributes a -1 charge and with 3 chlorine ions the total anionic charge is -3 to balance this in the neutral compounds. Iron must be iron 3 plus consistence with its common plus 3 straight in covalent ionic halides. These compounds, a yellow solid, acts as a Lewis acid and catalyzed in organic synthesis. What is the significance of inert gases in lightening? Inert gases like neon emitting 600 to 700 nanometer red orange light and argon with mercury vapor for 254 nanometer UV converted to visible light by phosphorus field fluorescence and neon tubes. When an electric current excites their electrons to higher states, they release protons upon returning to ground states, providing efficient, long-lasting illumination for sign displays and energy saving bulbs, leveraging their inertness to pavements filaments burnout. How does the size of a lanthanide ion change across the series? Lanthanide ions exhibit the lanthanide contraction where the ionic radius decreases from cerium 3 plus 1.034 angstrom to lutetium 3 plus 0.848 angstrom across the series. This results from the pore shielding of 4f electrons, allowing the increasing nuclear charge Z is equal to 58 to 71 to pull electrons closer, reducing ionic size. This effect impacts chemical similarity, separation difficulty, and applications like smaller Lu3 plus in phosphor versus large Ce 3 plus in catalyzed. What is a ligand in coordination chemistry? A ligand is a molecule or ion with one or more lone pairs of electrons that can donate to a metal ion, forming a coordinate covalent bonds. Example include monodentate ligands like NS3 via N for Cl minus and polydentate ligands like ethylene diamine En, bidentate or EDTA hexadentate ligands determine the complex geometry, stability via acylation and reactivity, playing a key role in inorganic systems. Example H2O in hemoglobin and industrial catalyzed. What is the primary source of teens? Primary source is cassiterite, a mineral mined in countries like China and Indonesia. The extraction process involves crushing and roasting cassiteracin to remove impurities, followed by reduction with carbon in a lever river laboratory furnace at 1200 to 1300 degrees Celsius, producing molten tin. This tin is refined by boiling or electrolysis, yielding a metal used in a shoulder tin lead. Tin plate is still coating and bronzy alloys. How do halogen reacts with alkali metals? Halogens reacts exothermically with alkali metals to form ionic halides due to electron transfer from the metals valence electron to the halogens vacant orbitals. For example, to Na solid plus Cl gas is equal to NaCl gas to NaCl solid produce sodium chloride with sodium donating its 3s1 electron to Cl chlorines 5p 3p5 forming sodium plus and chlorine minus reactivity decreases down the halogen group fluorine better than iodine due to stronger XX bonds, but all reactions are vigorous. All reactions are vigorous, often with flame and explosion under a heat. What is the role of lead in industrial applications? Lead is extracted from galena PBS by roasting to lead oxide PBO, then reduced with carbon in a blast furnace at 1000 degrees Celsius. 1000 degrees Celsius it's a high density 11.34 gram per centimeter cube, and corrosion resistance make it ideal for lead acid batteries, plumbum and PbO2 electrodes. Radiation shielding example in X-ray rooms and historical plumbing pipes. Though its toxicity high shifted focus to safer alternatives like PVC with strict regulations on its use. What is the optical isomerism? In a coordination of compounds, optical isomerism occurs when a coordination of compounds exist as superimposable mirror image in Marshall lacking an internal plan of symmetry. COEN 3 plus this isomers rotate plan polarized light D or I forms D or L forms with applications in chiral catalysis and pharmaceutical example resolving rhythmic mixture. The phenomenon depends on the ligands, special arrangements and metals coordination numbers. Typically 6 for octahedral complexes. Why are lanthanides used in magnets? Lanthanides like neodymium Nd and samarium SM are used in magnets. Nd2Fe14B SmCO5 due to unpaired 4f electrons creating a strong magnetic moments and high anisotropy. Neodymium magnets with a maximum energy products of 50 mGoE are critical in electric motors. Wind turbines and hard drives. While samarium cobalt magnets resist demagnetization at high temperature, used in aerospace and military applications. What is the electronic configuration of a typical transition metals. Atypical transition metals like iron Fe is equal to Z26 has an electronic configuration of argon 3d6 4s2, where the 3d orbitals are partially filled, enabling multiple oxidation states plus 2 plus 3 and complex formation. The 4s or orbital fails before 3d due to lower energy, but 4s electrons are lost. First, in ionization, example Fe2 plus argon 3d6 a characteristics feature driving their catalytic and colorful properties in chemistry. How is argon used in welding? Argon is used as a shielding gas in tungsten, inert gas, and metal inert gas MIG welding. It forms a protective blanket around the weld folds, preventing atmospheric oxygen and nitrogen from causing oxidation or nitride formation, which weaken the joint. Its high density 1.78 g per gram per liter and inertness ensure a stable arc and clean welds, particularly for reactive metals like aluminum and titanium, enhance structural integrity. What is the stability order of halide complexes of transition metals? The stability order of halide complexes iodine, bromine, chlorine, fluorine increases with ligands, electronegativity and charge density. Fluoride with the highest electronegativity 3.98 and smallest ionic radius 133 pm. 133 pm forms the strongest complexes. Example TiF6 2 minus log K is equal to 20, while iodides larger size 220 pm and lower charge density weaken bonding. Example til 6 2 minus is less stable. These trends reflect hard soft acid based theory with F minus as a hard base, preferring hard metal ions. What is the role of xenon in medical imaging? Xenon 133 a radioactive isotopes with a 5.24 a day half-life is used in lung ventilation studies and imaging. Patients inhale it as gases and its gamma emissions 81 keV kilo electrovolt are detected by gamma cameras to map airflows and diagnose conditions like pulmonary embolism or chronic obstructive pulmonary disease. Its inertness ensures safety, while its solubility in blood aids distribution, making it a precious diagnostic tool in nuclear medicine. What are alkali metals and where are they located in the periodic table? Alkali metals are a group of highly reactive elements found in group 1 of the periodic table, which includes lithium, sodium, potassium, rubidium, cesium, and francium. These elements are located on the far left side of the periodic table, excluding exploding hydrogen. Their high reactivity stems from having a single valence electrons in their outermost shell, which they readily lost to form plus one ions, making them strong reducing agents. This reactivity increases down the groove due to decreasing ionization energy and increasing atomic size. What are alkaline earth metals and what makes them different from alkali metals? Alkaline earth metals are elements in group 2 of the periodic table, including beryllium, magnesium, calcium, strontium, barium, and radium. Unlike alkali metals, which have one valence electrons, alkaline is metals have two valence electrons, leading to a blast to oxidation states. This makes them less reactive than alkali metals because of the second electrons is held more tightly, requiring more energy to remove. However, they are still reactive, forming ionic compounds with non-metals, and their reactivity increasing down the group. Hot elements are included in group 3A, 7A of the periodic table. Group 3A through 7A, also known as group 13 to 17 in modern UPAC numbering, including a diverse set of elements, boron and aluminium. In group 3A, carbon, C and silicon. In group 4A, nitrogen and phosphorus in group 5A, oxygen, sulfur in group 6A, and halogens, fluorine, bromine, iodine, and astatine. In group 7A, these elements exhibit a wide range of chemical behaviors from metalloids, boron, silicon to non-metals, oxygen, nitrogen, and highly reactive halogens due to varying numbers of valence electrons from 3 to 7. Why are halogen highly reactive? Halogens are located in group 17 are highly reactive because they have 7 valence electrons, leaving them 1 electron short of a stable octet. These electrons configuration derives them to gain 1 electron or share it to achieve stability, often forming -1 ions. Example, fluorines. Their reactivity decreases down the group of fluorine, bromine, iodine due to increasing atomic size and decreasing electronegativity. But all halogens readily reacts with metals and hydrogen to form compounds like sodium chloride and HCl. What is metallurgy and what is its purpose? Metallurgy is the branch of science and technology focused on extracting metals from their naturally occurring bodies and refining them into usable forms. Its purpose is to isolate pure metals, iron, copper, from mineral compounds, often involving processes like roasting, smelting, or electrolysis. This enables the production of materials for construction, electronics, and other industries, while also studying the physical and chemical properties of metals to optimize their applications. How is magnesium extracted from its ore? Magnesium is primarily extracted from ores like magnesite MgCO3 or dolomite CaMgCO3 through a multi-step process. First, the ore is calcined to produce magnesium oxide MgO. This is then converted to magnesium chloride MgCl2 by reacting with chlorine or ammonium chloride. Finally, electrolysis of molten MgCl2 in a cell. Example, the Dewey process separated magnesium metals at the cathodes with chlorine gas released at the anode, yielding pure magnesium for use in alloys in lightweight materials. What is the primary ore for aluminium, and how is it processed. The primary ore for aluminium is bauxite, a mixture of aluminum oxides and hydroxide. The extracted process begins with the Bayer process, where bauxite is digested with sodium hydroxide to dissolve aluminum hydroxide, which is then precipitate as alumina Al2O3. This alumina is purified and subjected to the Hell-Héroult process, an electrolytic method using a molten cryolite bath, where aluminum is reduced at the cathode and oxygen is released at the anode, producing pure aluminum for industrial use. How is iron extracted from its ore? Iron is extracted from hematite Fe2O3 or magnetite Fe3O4. Ore is using a blast furnace. The process involves charging the furnace with ore, coke, carbon, and limestone CaCO3. Hot air is blown in, causing coke to burn and produce carbon monoxide, which reduce iron oxide to molten iron. Limestone decompose to form sludge, which removes impurities. The molten iron is trapped off and further refined into steel or cast iron for construction and manufacturing. What are the common oxidation states of transition metals? Transition metals are found in the D block groups 3 to groups 12. Exhibit multiple oxidation states due to the ability of d electrons for bonding. For example, iron shows +2 and +3 states. Copper Cu shows +1 and +2, and chromium can be +2, +3, and +6. This variability arises because d electrons can be lost or shared, allowing transition metals to form diverse compounds like iron chloride and FeCl3, which are crucial in catalysis, and chlorine agents. What is aqueous chemistry in the context of transition metals? Aqueous chemistry of transition metals involve the behavior of their ion in water, where the often form hydrated complexes Fe2O6 3+. These include studying their solubility, acid base properties, and redox reaction. The presence of water ligands can stabilizing certain oxidation states, and reaction with other ligands in history can lead to color change or precipitation, making aqueous chemistry key to understanding their coordination behavior. What are oxides and halide of transition metals? Oxides are compounds formed when transition metals reacts with oxygen, such as Fe2O3, rust, or CrO3, exhibit colors and magnetic properties based on oxidation states. Halide results from reactions with halogens, example FeCl3 or TiCl4, and can be covalent or ionic depending on the metal charge. These compounds are important in industrial applications like pigments, Cr2O3, or catalyzed TiCl4 in Ziegler and naphtha polymerization. What are lanthanides, and where are they found in the periodic table? Lanthanides are the 15 elements from cerium Ce, atomic number 58, to lutetium Lu71, located in the F block at the bottom of periodic table. They follow lanthanum La and are characterized by the progressive filling of 4f orbitals. Despite their similar properties, due to lanthanide contraction, they are used in magnets, lighting, and alloys. Because of their unique electronic configurations. How are lanthanide isolated? Lanthanides are isolated from monazites or bastnasite ores using using a complex processes due to their similar chemical behavior. The uri is digested with acid to form soluble salt, followed by ion exchange chromatography or solvent structure. This method separated lanthanides based on slight differences in ionic radius and complexation, producing pure elements or compounds for industrial use. What are aquo ion and oxo salt in lanthanide chemistry? Aquo ion are hydrated lanthanide ion such as CeS2O 8 3 plus or GdS2O 9 3 plus formed when lanthanides dissolve in water. With the coordination numbers varying with the ionic size. Oxo salts like lanthanide, oxalates or nitrates. Results from reactions with oxo acids often used as intermediates in purification. These compounds reflects the lanthanides' preference for high coordination and oxygen donor ligands. What is a coordination compound? Say a coordination compound is a complex where a central metal ion or atom is surrounded by ligands molecules or ion with lone pairs. Example NS3 Cl minus forming a coordination covalent bonds. Example include CO NS3 6 Cl3. Where cobalt is the central ion and ammonia ligands coordinate to it. These compounds are vital in catalyzed medicine and biological systems due to their stability and reactivity. Who developed the nomenclature for coordination compounds? Alfred Werner, a Swiss chemist, developed the nomenclature and structural theory for coordination compounds in the early 20th century. His work earning him the 1913 Nobel Prize. Introduced the concept of primary and secondary valency, laying the foundation for understanding their bonding and isomerism, which are still used in modern chemistry. What is Warmer's primary valency concept? Warmer's primary valency refers to the oxidation states of the central metal ion equivalence to the number of negative charges is valency in a coordination compounds. For example, in CONH3 6 Cl3, the primary valency of CO3 plus is 3, missing the 3 chlorine ions outside the coordination spheres, reflecting the ionic bonding aspect of the complex. What is a secondary valency in coordination compounds? Secondary valency or coordination number is the number of ligand donor atoms directly bonded to the central metal ions. In CONH3 4 2 plus, the secondary valency is 4, as 4 nitrogen atoms from NH3 ligands coordinate with copper. This determines the geometry, example tetrahedral or octahedral, and stability of the complex. What is Seedweg electronic concept? Seedweg electronic concept proposed by Neville Seedweg explains coordination compounds bonding through the donation of electron pairs from ligands to the metal ions. Empty orbitals forming dative bonds. This donor acceptor model complements Warmer theory in emphasizing the role of ligands electrons in stabilizing complexes like NiCO4. What is valency bond theory in coordination chemistry? Valency bond theory (VBT) describe a coordination compounds formation by the overlap of ligand orbitals with lone pairs with the metals vacants hybrid orbitals. Example DS P2 or D2sp3 for CONH3 6 3 plus. Cobalt 3D 4s and 4p orbitals hybridize to accommodate 6NH3 ligands, explaining the octahedral shape and stability, though it has limitations with magnetic properties. What factors affect the stability of coordination compounds? Stability depends on the metal's ions charge and size, ligands strengths. Selecting ligands like EDTA enhance stability via the silage effects. The conditions like pH or temperature, high charge density metals, CO3 plus and strong field ligands. Example CN minus form from stable complexes, influencing their use in analytical chemistry and medicine. What is isomerism in coordination compounds? Isomerism in coordination compounds occurs when compounds with the same molecular formula have different arrangements. Type include geometric cisterns in PTNS3 to Cl2, optical non-superimposable mirror image like COEN3 3 plus and linkage e.g. example CONS3 5NO2 2 plus versus CONS3 2 NS3 5ONO 2 plus, reflecting diverse spectral possibilities. How are coordination compounds used in biological systems? Coordination compounds are essential in biology. Example hemoglobins, iron center binds oxides and chlorophyll magnesium 2 plus coordinates with porphyrin for photosynthesis. Vitamin B12 for coordinates ACE enzyme function, showcasing their role in oxygen transport, energy production and metabolic processes. What are inert gases and why are they called so? Inert gases or noble gases group 18 helium, neon, argon, krypton, xenon, radon are called so because their fields S and P orbitals. Example neon 1s2 2s2 2p6 makes them chemically stable and unreactive under normal condition. Their lack of a tendency to gain or lose electron limits compounds formation, though exceptions like xenon fluoride exist with strong oxidants. What are some applications of inert gases? Inert gases have diverse use. Helium for cryogenics and balloons. Neon for illuminated science. Argon for welding shells. Krypton in lasers. Xenon in medical imaging and radons in cancer therapy. Their inertness prevents unwanted reactions, making them ideal for controlled environments and specialized equipments. Why does xenon show some chemical reactivity? Xenon's larger atomic size and available 5d orbitals allow it to overcome its inertness, forming compounds like xenon fluoride, XeF4 and XeO3 with highly electronegative elements fluorine and oxygen under strong conditions. Example electric discharge. This reactivity is unique among noble gases due to its polarizability and electron accessibility. What is the general trends in reactivity of alkali metals? Reactivity of alkali metals increases down group 1 lithium to Cgm because ionization energy decreases with increasing atomic size and reduced nuclear attraction on the valence electron. This makes Cesium more reactive than lithium, as seen in their vigorous reaction with water, producing hydrogen gas and metal hydroxide. Example 2CH 2 Cesium plus 2H2O is equal to 2CHOH plus H2. How are chromium and nickel extracted? Chromium is extracted from chromite FeCr2O4 by roasting with sodium carbonate to form sodium chromite, then reduced with aluminium in the aluminothermic process to yield pure chromium. Nickel is extracted from landite, nickel iron 9 sulfur 8 by roasting to oxides, following by smelting and electrolysis, reducing nickel for alloys and batteries. What is the role of copper in metallurgy? Copper is extracted from chalcopyrite CuFe S2 through smelting to remove iron and sulfur, followed by electrolytic refining to produce high purity copper. Its excellent electrical and thermal conductivity makes it essential for wiring, electronics and plumbing with global demands, driving efficient extraction method. What are the common oxides of lanthanides? Lanthanides form stable oxides like CEO2, cerium 4 oxide, used in a catalysis, Nd2O3, neodymium oxide for glass coloring, and La2O3, lanthanum oxide in optics. These oxides results from burning lanthanides in oxygen, exhibiting high melting points and unique electronic properties due to 4f electrons. What is the coordination number in CuNS3 for 2 plus? The coordination number in CuNS4 NS4 2 plus is 4 as 4 ammonia NS3 molecules act as ligands, is donating a lone pair to the Cu2 plus ion. This typically results in a square planar geometry common for Cu2 plus complexes and reflexes the metals, prevents for coordination bonding. What is a Select effects in coordination chemistry? The Select effects in the increased stability of coordination compounds with multi-dentate ligands, ethylene diamine EDTA, that form multiple rings with the metal ions. This entropy driving effects arises because selection releases more water molecules than monodentate ligands, enhancing stability as seen in IEN3 2 plus compared to NS3 6 2 plus. How do actinides differ from lanthanides? Actinides, thorium and lower cerium differ from lanthanides by its more radioactive due to unstable nuclei, exhibit oxidation states from +3 to +6 and having 5f electrons that are more diffuse, affecting bonding located after actinium. They are used in nuclear fuel uranium PU. Unlike lanthanides, magnet applications. What is geometric isomerism in coordination of compounds? Geometric isomerism occurs when ligands occupy different spatial positions around the metals. Example in PTNS3 2Cl2, the cis isomers has Cl ligands adjacent, while the trans has them opposites. These affect physical properties like color and reactivity with applications in chemotherapy. Cisplatin. What is the role of zinc? In metallurgy, zinc in metallurgy, zinc is extracted from sphalerite zinc sulfide by roasting to zinc oxide, then reduced with carbon or electrolyzed from zinc SO4. Its primary role is galvanizing iron to prevent corrosion, forming a protective zinc layer, and it's also used in alloys like brass and die casting. Why are transition metal oxides colored? Transition metals oxides are colored due to d electron transition in the metals, partially fields d orbitals influenced by elegant fields. For example, CO2 plus in CuS2O6 2 plus absorbs red light appearing blue. The specific color depends on the oxidation states and ligand strengths, making them useful as pigments. What is the oxidation states of iron in FeCl3? The oxidation states of iron in FeCl3 is plus 3 is chloride ion, Cl minus chloride ion contributes minus 1, and with 3 chlorine chloride ions, the total charge is minus 3, which is valenced by Fe3 plus confirming irons plus 3 straight in this covalent ionic compounds used as a catalyst. What is the significance of inert gases in lightning? Inert gases like neon red, orange glow, and argon with mercury vapor for white light field fluorescence, and neon tubes. When electrified, they emit light through excited electron transition, offering energy efficient illumination for sign display and household lighting due to their inertness and stability. How does the size of a lanthanide ion change across the series? Lanthanide ion exhibit the lanthanide contraction, where ionic radius decreases from Ce3 plus 1.034 angstrom to Lu 3 plus 0.848 angstrom due to pore shielding by 4f electrons. This increases nuclear charge pull electrons closer, affecting their chemical similarity and separating challenge. What is a ligand in coordination chemistry? A ligand is a molecule or ion with lone pair. Example: NH3 Cl minus is 2O that donate electron to the central metal ion, forming a coordinate bond. Ligands can be monodentate, one donor atom, or polydentate, EDTA influencing the complex geometry, stability, and reactivity. What is the primary source of tin? Tin's primary source of cassiterite is NO2, mined globally and proceed by roasting to remove impurities, then reduce with carbon in a laboratory furnace at high temperature to produce molten tin, used in solder and tin plating. How do halogen reacts with alkali metals? Halogen reacts vigorously with alkali metals to form ionic salts due to electron transfer. For example, 2Na plus Cl2 is equal to 2NaCl, where sodium donates its valence electrons to chlorine, forming sodium plus and chlorine minus ions. Reactivity decreases down the halogen group due to increasing bonds strength. What is the role of lead in industrial applications? Lead is extracted from galena PBS by roasting to PBO, then reduced with carbon. Its high density and resistance to corrosion make it ideal for lead acid batteries. Radiation shielding, example X-ray room, and his historically plumbing so its toxicity limits modern use. What is optical isomerism in coordination compounds? Optimal isomerism occurs when coordination compounds like COEN3 plus exist as a non-superimposable mirror image in an tumors lacking a plan of symmetry. These isomer rotate pan polarized light dextroratory laboratory with applications in asymmetric synthesis and pharmaceuticals. Why are lanthanides used in magnets? Lanthanides like neodymium, Nd, and samarium SM are used in magnets. Example NdFe due to unpaired 4f electrons creating a strong magnetic moments. They are high coercivity and remnants make this magnet essential in electric motors, wind turbines, and hard drives. What is the electronic configuration of a typical transition metals? Atypical transition metals like iron Fe atomic number 26 has an electronic configuration of argon 3d 6 4s2. The 3d orbitals are partially filled, allowing multiple oxidation states and complex formation, while the 4s electrons are lost fast during electrons. A hallmark a transition metals chemistry. How is argon used in welding? Argon is used as a shielding gas in welding, TIG welding, to create an inert atmosphere around the weld fold, preventing oxidation and contamination by atmospheric gases like oxygen or nitrogen. Its high density and non reactivity ensure a clean strong weld. What is the stability order of halide complexes of transition metals? The stability order of halide complexes iodine, bromine, fluorine increases with ligand electronegativity and charge density. Fluoride being the most electronegative forms the strongest complexes PIF6 2 minus, while iodide larger size and lower charge density. We can say its bondings. What is the role of xenon in medical imaging? Xenon 133 133 a radioactive isotope. A radioactive isotope is used in lung ventilation studies and imaging inhaled as a gas. Its gamma emissions are detected by scanners to assess airflow and diagnose conditions like pulmonary embolism, leveraging its inertness and short half-life, 5.24 days.